Hello, and welcome to another edition of Math, Music, and More. I've been getting kind of a kick out of noodling around, as I like to say, with the Laplace transforms, and I was able to derive some interesting relationships based on taking derivatives and trying to solve for the Laplace transform of certain polynomials to arrive at these recursive relationships. But then I realized I never really got into detail as to why Laplace transforms are so powerful and so useful and what they're actually used for. So today, in today's video, now I'd like to walk through with you some early context settings, some simple ordinary differential equations, how they work, and how we don't quite need Laplace transforms yet with the examples that I'll show you. But as you'll see in a moment, I'm only going to share with you the simplest of examples based on just two things: separation of variables and proof just by inspection, because it's just sort of intuitively obvious when you look at the equations. But you'll notice very quickly, there are not going to be a lot of ODEs, ordinary differential equations, that are always going to fall into one of those two camps. Either it can be solved by separation of variables or by just inspection. So let's go through those just that we can work through them together. And then in the next video, I'll actually give you an example of one where those two methods would never work, and yet Laplace transform gives us such a beautiful and simple solution. So let's jump right in. The first, I think, classical example is a first order ordinary differential equation. In other words, we only take one derivative, and we can talk about a very simplistic model of population growth. If we let, for example, capital N represent the size of a population, we could say something like the rate of change of the population, dn dt, would just be directly proportional to the number of entities, whatever species that might be, that actually exist at that point in time, t. And that makes a lot of sense. But then when you look at it for the first time, you're like, yeah, but how do I actually create a function n of t? Well, here we use, again, the classic simplest tool, which is separation of variables. And what we do there is, all we do is pull the dt over to this side, right? And watch this, pull the n over to this side. We just flip things around a little bit. And now we can actually integrate both sides. And if you take the integral of 1 over n with respect to n, then the answer is clearly just the natural logarithm of n, because we know that the derivative of the natural logarithm of n is 1 over n, and hence the inverse would count here. As far as the integral of k dt, well, k we're presuming is a constant of proportionality, and hence the integral of dt, again, is just simply t. So therefore, it has to be equal to kt. And therefore, n is a function of time now. And how do we get nt on its own? We got to figure out a way how to get rid of the ln. Well, that's easy. We just take this whole thing and raise both sides, or use a base of the natural, inverse of the natural log e, and these things sort of cancel. So you're therefore left with a simple equation. The population as a function of time is just equal to e to the kt. Notice that I've kind of ignored the constant of integration, because we always have constants when they're indefinite integrals. But that's actually pretty easily solved, because instead of e to the kt, you could say it's whatever your initial population is times e to the kt. And there's your answer. So there's one example of separation of variables. And I hope that suffices. You may sometimes look at problems and not realize that separation of variables could actually work. So let's work on a problem in aerodynamics, for example, or projectiles. You could say that the force on a projectile that's being shot perfectly horizontally is just the braking force of air against it. And that is, again, since it's in the negative direction against the actual path of the projectile, it would be negative k times the velocity at that point in time. And velocity we could think of as the derivative of x with respect to time. And I'll mark that this time as x dot. And if we want to represent force in terms of a differential equation, well, we just use, obviously, F equals ma. But instead of calling it a, we say it's the second derivative with respect to x. And again, I'm just using a different notation here, but it's quite common. So m times x double dot is negative k times x dot. And you might say, well, there we can't really do separation of variables. Oh my gosh, how do we solve this problem? No, you can. And this is a great example of when you take a step back and think about what the problem is actually about, you can use separation of variables and come up with a very simple solution. For example, what's another way of thinking of x dot? We could just call it the velocity. So represent x dot by v. Well, what is x double dot? It's acceleration. It's the second derivative with respect to position, or x, but it's actually the first derivative with respect to velocity, not the second. So now we have mv dot equals negative kv. Now we can start monkeying around with separation of variables, because we know that v equals dx dt, but we're going to ignore that. We're going to say that v dot equals dv dt. So let's just do that substitution, and we bring m over to the other side. So we'll say that dv dt, bringing the m over, is negative k over m times v. And look, now we have a problem that's very, very similar to the population growth problem that we did before. Only instead of positive, it's negative. And instead of just a constant of proportionality, it's the constant divided by the mass of the object that is acting as the projectile. So again, we do separation of variables. We bring the v over here, and we bring dt over here. And now if we integrate both sides, we basically get that the ln of v must be equal to negative k over mt. And if we use the e trick again, we simply get that v equals e to the negative km over t, where if we include, again, constants are always necessary with indefinite intervals. Here, I'll put the constant right now up there, and I'll call it v naught. In other words, the velocity at time t equals 0. So this is a great equation, because let's think about like the intuition behind this. At time t equals 0, you have the muscle velocity, right? That means at t equals 0, this thing goes to 1. And what do you get? You get v naught. You get that initial velocity. But with every second that passes, you get that negative curve of the decline of a negative exponential curve, which is interesting because if you picture a negative exponential, it starts very steep in the negative direction and then it flattens more and more, which kind of makes sense intuitively because as it slows down, there's less and less drag acting against that projectile. Let me give you just one example, please, of just things that are intuitive by inspection. And I'll use, I'll actually use Hooke's law. So Hooke's law refers to if you have like a wall with a spring attached to a block and you pull the block out a distance x, then because of that, tension in the spring, how would the block actually, move back and forth once it's released and there are no external forcing, force functions applied to it and it's just freely moving back and forth. Well, Hooke's law just says that the force has to be equal to, again, negative k times the actual amount that you've displaced the block. And why is it negative? Because if I pull the block in this direction, the force is pulling it back in the opposite direction. So always think intuitively about the problem so you know when to use negatives and not to use negatives. And again, we represent m as, force as m times x double dot equals negative kx. We can bring the m over again and we can say x prime equals negative k over mx. So the interesting thing is, we don't really have to think about it that long to think about what function could you take the derivative of twice and almost get the same function back. You just have a negative factor multiplied by it. It's a transcendental function. You know that if you have something like the sine of t and you take the derivative once, you get the cosine of t. If you take the derivative again, in other words, you've done it twice now sequentially, you get negative sine of t. So the second we see a negative sign being invoked from a double derivative, we know that it has to be either a sine or a cosine, because a cosine function does something similar. Cosine of t becomes negative sine of t, which then becomes negative cosine of t. So you get the same function back as a negative. The only thing that we notice here is that there's a factor out front. So what does that mean? Easy, we just take the square root of that. We say that x of t basically has to be equal to either, a times, because it's constant again, a times the square root of k over m times time, or plus b times the cosine of square root of k over m times time. That whole thing is in the argument. So this is a perfect example of, if you're kind of used to taking derivatives and you know how some of the classic functions behave, You don't have to do some complicated solution. You just look at it and you kind of know the answer. Sometimes it'll just be a sine wave. Sometimes it'll just be a cosine wave. Sometimes it will be a linear combination or superposition of the two. It all depends on the initial conditions. At t equals 0, what's the position of the block? At t equals 0, what's the velocity of the block? Do you start pulling it out with no velocity? Or do you start with it passing at 0 but with a certain velocity? That'll help you figure out what actually the constants of A and B are. It's all about initial conditions. But look how simple these ODEs are that I just covered with all of you. Incredibly simple. Once you start putting in more terms, second order differentials where you have a second derivative and a first derivative and a forcing function, et cetera, these simple tricks, like just knowing it based on inspection or separation of variables, are suddenly not going to work anymore. So I hope this was already a little bit eye-opening as to how quickly you can solve ODEs, even ones that at first blush seem a little more complicated. You can sometimes convert them into something where separation of variables or intuition just works. But in the next edition, the next episode, I'll actually go through a slightly harder problem where suddenly all these methods fail and the magic of Laplace transforms appear. Anyway, until then, I hope you liked it. Like and subscribe, and until next time, take care, everyone.